Hello students, so today we are going to move forward and calculate the kinetic potential and total energy of an electron revolving around the nucleus in the nth orbit of an hydrogen-like species. So this video is in continuation with the other two videos where I have derived the expression for radius and velocity of the electron revolving around the nucleus in the nth orbit using the Bohr model. So here I have also written the expression for radius and velocity of the electron in the nth orbit, which I have derived in my previous two videos. So let's start and assume that we have an atom and or ion. This can be, and this is a hydrogen like species. As I have explained before, hydrogen like species has only one electron in its orbit. So it can be any atom like hydrogen atom, or it can be ion like helium plus ion, Li double plus ion, or beryllium triple plus ion. So here I am going to draw a diagram. So this species has Z atomic number, so the total nuclear charge will be plus Ze, and the electron here that has minus E charge, and this electron has mass m and revolving with velocity v around the nucleus, and the radius of the orbit that is Rn. So basically here we have to find the kinetic energy, potential energy, and the total energy of the electron. So let's start with the kinetic energy. So kinetic energy K, let's say write kinetic energy K. As you know, that formula for kinetic energy for a particle of mass m moving with speed v is given by half mv square. So let's put the values here. Half m and v square means speed square. Speed expression I have written here. So I will put this value. So this is z square divided by 2 epsilon naught nh and this whole square. So from here we will get kinetic energy K is equal to, if I will open this square, I will get m z square e to the power 4, right? And this whole thing divided by, this will be 2 to the 4 and 2 8, so it will be 8 epsilon naught square n square h square. And let's write, this is your equation 1. So this is our first expression we wanted to derive. This is the expression for kinetic energy of the electron revolving around the nucleus in hydrogen like species. So now next step we will calculate the potential energy of the electron. So let's write the potential energy by symbol U. So potential energy using the Coulomb's law, the formula for potential energy of a two charge system is defined as 1 upon 4 pi epsilon naught product of the charges, means q1 q2, divided by separation between charges. So here the charges are plus Ze, the nuclear charge, and the electronic charge minus E. So here I will put the charge values with sign because potential energy is scalar quantity, and we need to put the sign of the charges also along with their magnitude. And this whole thing divided by separation between the charges is Rn, that is the radius of the orbit. So if we put the value of R here, then we will get 1 upon 4 pi epsilon naught, and this will be minus, because plus Ze minus E will be minus Ze square, and this whole thing divided by radius value, that is epsilon naught n square h square, and this whole thing divided by pi m z e square, and bring this denominator into numerator and it will become, and you can cancel the terms which are getting cancelled. So pi will get cancelled here, pi, and anything else, no. So this mze square will come into numerator, so it will become m z square e to the power 4, and this whole thing divided by, and this will be with minus sign, and this whole thing divided by 4 times epsilon naught into epsilon naught will be epsilon naught square n square h square. So from here we get the final expression for the potential energy. So we get potential energy expression U is equal to minus m z square e to the power 4 and whole thing divided by 4 epsilon naught square n square h square. So here E is the electronic charge, this is 1.6 into 10 raised to the power minus 19 coulomb. Z is the nuclear charge or atomic number of the species we have taken. M is the mass of the electron, which is 9.1 into 10 raised to the power minus 31 kg. Epsilon naught is the permittivity of free space, which is 8.85 into 10 power minus 12 coulomb square per Newton per meter square. N is the sequence number of the orbit or the nth orbit we have mentioned. So N is like 1, 2, 3 for first, second, or third orbit. H is the Planck's constant. So if you compare the two equations, this potential energy equation, let's write it is equation 2. If you compare equation 1 and 2, you can see that all the variables have same exponent, like m has exponent 1, z has exponent 2, e has exponent 4, epsilon naught has exponent 2, n has exponent 2, and h also has exponent 2. So in both the expressions, the exponent of each of the variable like mass, nuclear charge, electronic charge, that should be same. That's one thing to check. Okay. So if this is same, we can proceed further to get the total energy of the electron. So now we will write total energy E of the electron in the nth orbit. Let's write it En, and we can put here also Kn and Un. This is the kinetic and potential energy of the electron in the nth orbit. So similarly, total energy of the electron in the nth orbit En will be kinetic energy plus potential energy, because no other type of energy is here. So let's add these two. So if you can take the common terms, so we can take mz square e to the power 4, this whole thing divided by not 8, we can take 4 common, epsilon naught square n square h square, and inside bracket we will have 1 by 2 here because it is 8, so it will be 1 by 2, and minus here it will be total 1. So and what will it will be, half minus 1, it will be minus half, and if you can multiply the outside term with minus half, it will become minus mz square e to the power 4, and this whole thing divided by 2 into 4, it will become 8 epsilon naught square n square h square. This is the total energy En of the electron in the nth orbit. Okay. So yeah, so this way we got the expression for all the three types of energy. And one important thing to note here is that if you compare equation 1, equation 2, and let's say this is equation 3 we have derived right now, if you compare these two, you can say that total energy En is just equal to the kinetic energy if we ignore the minus sign. So you can say that En is equal to minus times Kn. And further, En, if you compare En and Un by equation 2 and 3, you see that here it is 4, here it is 8. So En basically it is Un divided by 2, right? So this is the relation between all these three types of energies: kinetic, potential, and total energy. And so you know that if we know any of these three values, En, Kn or Un, you can find the other two. This is a very important thing to remember. And let's move further. So here we can simplify this and we can write it in another form, the total energy. So we have En is equal to minus mz square e to the power 4. So we will write it minus we can multiply mz square e to the power 4, this thing divided by 8 epsilon naught square n square h square. Okay, so this we have, but we will write few terms outside this. So we will take z square outside and n square also outside. So what it now will be, so it will be here z square divided by n square, and it will be m e to the power 4, right? So minus m e to the power 4 upon 8 epsilon naught square h square. So we will compare here, we will multiply the numerator and denominator both by h into c. Okay, and so now it will be minus m e to the power 4 and whole divided by 8 epsilon naught square h cube into c. We will take this together, and then this is h into c into z square divided by n square. And I will tell you why I am doing all this. So this whole thing I have written in the bracket. This is actually given a specific name. This is given Rydberg constant. So it becomes Rydberg constant capital R h c into z square divided by n square. So this is a short notation for the energy formula of electron in the nth orbit. So here I will tell that R is equal to m e to the power 4 and whole divided by 8 epsilon naught square h cube into c. This is known as Rydberg constant. I have told about this constant before also. So this is Rydberg's constant. And what is its value? Value of R, as I have told before, this is 1.09 into 10 raised to the power 7 per meter. You should remember this. So this is the final result. And one last thing I will like to tell you before going. So here you can do one thing. If you put the values of every constant, because whole all the values in this expression, you know the Rydberg constant, you know the Planck's constant, you know the speed of light, you know everything. So if you put those values, what you will get, and you convert that into electron volt, and I think you know that one electron volt is defined as 1.6 into 10 raised to the power minus 19 joule. So basically 1 electron volt is the kinetic energy acquired by an electron when it is accelerated through a potential difference of 1 volt. So if I put the values here are Hc and I convert the total energy in electron volt, then what you will get? You will get minus 13.6 into Z square divided by N square, and this value, as I told this will be in electron volt. So this is the final expression you can remember. En is equal to minus 13.6 Z square upon N square. So this is the expression I would expect that you will remember, because in my next video I will explain about the hydrogen atom spectrum and I will start from this expression only. So I hope you enjoyed this video, you understood the derivation of the energy of the electron in the nth orbit, and you also understood the origin of the Rydberg constant, from where it comes. So I hope you are enjoying. So keep liking my videos, subscribe my channel and share videos with your friends also. And you can also post your questions and comments in the videos. I would try my best to answer those comments. So thank you very much. Take care and bye bye.